In this video, you're going to get a 20-minute masterclass on vectors. Vectors are a foundational idea that you're going to need to apply to a lot of areas in physics. We're going to start with the basics, build up your concepts, and all your problem-solving skills so that you can be successful in physics. On the top of the screen, we have the 4 main areas that we need to cover to understand vectors and be able to do all the problem-solving necessary for physics. The first thing to know is, what is a vector? And it is anything that has a magnitude and a direction. The magnitude is typically shown a couple different ways. So it's either shown with the length of an arrow or oftentimes just with a number value associated with whatever you're measuring, say for example 10 meters for a distance. For the direction, it could be something like up, down, left, or right, or it could be something like north, south, east, or west. And you'll see a bunch of examples of how we're going to use those different things. That basically covers our first question. Number 2, taking a look at vector addition / solving for an angle. So on the screen, we have 4 different vectors. I have this red one here. We'll call this one a unit of 5, this one 4, this one 8, and this one 2. And say, for example, all of these vectors are displacements. So we're going to go ahead and put a unit with them and call this 5 meters, 4 meters, 8 meters, and 2. I'm going to show you how to combine 2 of them in a more simple problem, and then I'll show you how to combine all 4 of them in a slightly more complicated one. So say, for example, you are combining the red and blue vector. Then we would go ahead and draw out your red vector, direction, and a magnitude. And the way we connect vectors or add them together is using something called a tip-to-tail method. So wherever one vector starts, wherever one vector ends, that's where the next one starts. So wherever the tip of one starts, the tail of another one begins, or wherever the tip of one ends, the tail of the other one begins. And then from there, all you have to do is identify the starting point and the ending point, and you connect those 2 together, and you have something called a resultant vector. And the resultant is basically the solution after summing up all your vectors together. Now, in a case like this, we have a nice little right triangle, which we're typically going to create, and we just need to find the hypotenuse of this right triangle. So we can just go ahead and use Pythagorean's theorem, a squared plus b squared equals c squared, where my hypotenuse is my c. So we're basically finding the square root of a squared plus b squared, and that's going to give us our hypotenuse. In this case, that's our resultant. So this one turns out to be pretty nice because we're going to take the square root of 4 squared plus 5 squared. That's going to be the square root of 16 plus 25, so that's going to give us 41. And then if we wanted to, we can put that into decimal form, and then we could call that 6.40 if you like to. Okay. Either way, depends on your preference or your teacher's preference, but we'll call that 6.40 meters. Now from there, if you wanted to, you can find a direction, which would basically be finding an unknown angle, so you can give the direction with a little bit more detail. Now what you do there is you're going to use inverse trig functions. Okay, so a lot of you are probably familiar with SOHCAHTOA, and if not, I'm going to break it down for you anyways. Now, in this case, I would typically do the inverse tangent, and the reason why I would do that is tangent is opposite over adjacent, and I originally have the opposite side in blue and the adjacent side in red, so that I'm taking the numbers that I for sure know are correct and then plugging them in. So I'm going to go opposite over adjacent, plug that into my calculator, and then I get an angle of 38.6 0.66 degrees. If you wanted to, you could use sine or cosine or inverse cosine because we have every single side of the triangle. In that case, for inverse sine, it would be the opposite end in blue, which is 4 divided by the hypotenuse, which if we want to be a little bit more exact, we'll call that square root of 41. If we wanted to use the inverse of cosine would be the a over the h, so adjacent over the hypotenuse. The adjacent side is the red side of 5. The hypotenuse is the square root of 41. Okay, it is completely unnecessary to do all three because you're going to get the same answer for all of them. So you can pick whichever one you like. I tend to use tangent. In a lot of cases, that's just my preference because, again, I'm using the original 4 and 5 as opposed to my solution of square root of 41. That is an answer that I solve for. And then that pretty much covers it for doing vector addition with an angle. But I'm going to show you one more slightly complicated example before we move on. All right, now what we're going to do is we're going to go ahead and we're going to add all these vectors. It actually doesn't matter the order in which you add them. So I'm going to go ahead and do the red vector first. Whoops. Red vector first. Here's the direction. Here's the magnitude. And then go ahead and put my blue vector on there. And then my pink one, I'm going to start it where the blue one ends, and it's basically going to trace it down. Whoops, that's not very straight. But that one's 8 meters down. My green one, start it where the pink one ends, just go back 2. And then my resultant vector is my final solution, which is connecting the starting and ending point. Now this one does look a little bit more complicated. What I'm going to do is I'm still going to turn it into a right triangle to simplify things for me. If I look at just this portion from here to here, the pink vector is a total of 8, but if you chop off this blue portion, it's basically 8 minus 4, which means this portion of the pink vector is going to be 4 as well. So I know vertically this distance is going to be 4 meters. And then the horizontal distance away I know is going to be 3 because the red one goes to the right 5 and then the green one brings it back 2. So we know that this horizontal distance is going to be 3. So what I can do is I can redraw my triangle 3 meters out to the side, 4 meters down, and then my resultant vector is just going to be that one right there. So that's a little bit of a trickier version. I won't go through all the steps again, but you would find the resultant by doing the Pythagorean theorem again. And that one actually comes out pretty nicely to the square root of 25, so that's just 5. And then you can find the angle using the inverse of tangent, sine, or cosine. All right, that covers it for the vector addition and solving for an angle. All right, now getting to the second two parts, we're going to be working with some angles now. So we have, say for example, some kind of velocity like 10 meters per second. That 10 could be a displacement, it could be a force, it could be a velocity, it could be whatever. In physics, once you get to some deeper problem solving, you're going to have some angled components. Okay, this one we're going to do the opposite. Instead of using some vertical and horizontal components and put them together, we have an angled component, and then we're going to go ahead and write out a horizontal and a vertical component to show us where our x and y vectors are, to show the horizontal and vertical components of the velocity. So if something is going up on an angle at 30 degrees at 10 meters per second, part of that 10 is causing it to slide sideways to the right, and then part of it is projecting it upwards into the air and affecting its height and hang time. So what we're going to do is use some trig functions, in this case just regular old trig functions, And we want to use something with the hypotenuse for sure because we have a hypotenuse of 10, and that would include sine and cosine. So the sine of theta is going to be the opposite over the hypotenuse, and then the cosine of theta is going to be adjacent over the hypotenuse. So if I wanted to solve for the y component, I would use sine because that's opposite of my 30, and then I would say sine of 30 degrees equals the opposite over the hypotenuse of 10. And then you just basically multiply both sides by 10. And that will give us 5 meters per second for my y component. As we go to the y component, or excuse me, the x component, we're going to do the same thing. We're going to do cosine of 30 degrees equals x over 10. And then multiply both sides by 10 again. And then we got 10 times cosine of 30 equals 8.66 meters per second. Okay, and one little mental check I like to do is 45 degrees is right in the middle where our x and y components would be the same. So 30 degrees is under 45, so it's more horizontal. So I'm expecting my x component to be larger than my y component, and 8.66 is definitely larger than my 5 meters per second. So that checks out. In case I make a silly little mistake, then I can kind of catch myself there. Okay, now most people, well, I wouldn't say most people, but a lot of people will say that you just always take your component and multiply it by sine for the vertical component, and a lot of people might say you take your hypotenuse and multiply it by cosine to get your horizontal component. Okay, that does work a very, very high percentage of the time, but I would do a quick mental check to make sure you are taking if you're solving for the opposite end, you use sine, and the adjacent side you use cosine. Okay, I'll show you one example where that doesn't actually work out, but it does work out a very, very high majority of the time, but I wouldn't expect that to work 100% of the time. Okay, so that's how you break stuff into components. You're going to use some trig and then complete a little right triangle with a horizontal and vertical vector. All right, our final problem or idea is combining angle vectors. So this one is going to be a little bit more complicated. We're going to use all the skills we had already used before and then kind of combine them all into one. So I have a vector of 10 meters per second at 30 degrees and one at 15 meters per second downwards to the left at 40 degrees. So I stole the 10 meters per second at 30 degrees from our previous problem. That way it will have saved us a little bit of work. So again, my x component there was 8.66 meters per second when I used cosine, and then my y component ended up being 5 meters per second when I used sine. So I'm going to do the same exact thing for this one. I'm going to go ahead and make a vertical component and a horizontal component. Okay, this one, based on where I put the 40 degrees, my opposite end of the 40 is actually my horizontal component. So that's where I said you got to be a little careful sometimes, although the very high majority of the time you will use sine for the vertical and cosine for the horizontal. So if that 40 happened to be up here and you made the triangle above this black line, then you would have used the regular sine and cosine as usual. All right, so for this one, I'm going to end up taking 15 times the sine of 40, because that's opposite for my x component, and that's going to give me 9.64. And then my blue side, my blue vector is adjacent to the 40 degrees, so if I take 15 times cosine of 40, that's going to give me 11.49. All right, so I have all of my vector components now. So you have to add up my vectors with the horizontals independently from the vertical ones. Okay, so I'm actually just going to draw this out one more time put the 5 over here, and then I'm going to go ahead and take my red one and put it over here. All right, so let's go ahead and combine our horizontal ones first, our red vectors. So we have a red vector going this way, 8.66, and then I have a vector going from the end of this one back this way, 9.64. Okay, if I do a bit of subtraction, my resultant ends up being a vector that's going to be a tiny bit this way, and that would just be 0.98. Okay, if they're in the same direction, you're going to add them. If they're in opposite directions, you're going to subtract them. Okay, no need to put a negative in there for the final answer. I just have an arrow pointing to the left because clearly this vector going to the left is larger than the one going to the right. Okay, so that is my final x component. Now for my vertical ones, I have one that goes 5 meters per second up, and then I have one that goes 11.49 meters per second down. Okay, again, these ones are in opposite directions. If they happen to both be pointing up, I would have added those vectors together, and I'd have a big 16.49 meter per second vector. But I'm going to end up subtracting them, and clearly the downward vector is a little bit larger, so I'm going to have a downward vector, subtract them, that is 6.49 as my final y component. Okay, so now that I have my final horizontal and vertical component, I can get my final answer. So I have my final x component. It was going to the left at 0.98. And then I have my final vertical component. That one goes down 6.49. Now from there, I'm going to go ahead and make my resultant vector as I did before. Go ahead and connect the starting point of my first vector to the end point of my final one, and then I could use a little Pythagorean theorem. And then I get an answer of 6.56. Okay, that is my final answer for the magnitude of my vector. Okay, now as far as the direction goes, I can go ahead and use the inverse sign. And then if I use the, actually I'll go with inverse tangent. So I'm going to go with inverse tangent, where it is the opposite end from it, which is the 6.49 divided by the adjacent 0.98, and that gives me an angle of 81.41 degrees. Okay, you could report that answer a bunch of different ways. Okay, so that specific angle right here, an unknown angle theta, is 81.41 degrees. You can also, in addition, call that 81.41 degrees south of west. Okay, the reason why you might put that is if you take a look at the cardinal directions, north, east, west, and south. Okay, this vector is to the west, and then if you tilt 81.41 degrees south of west, then that gives you the theta that we looked for. Okay, sometimes that's a common notation saying south of west or maybe north of east or something along those lines. Okay, again, depending on the preference of whoever is taking a look at your solutions. The second thing you might be able to do is, instead of just having this angle right here, we know all the way around from your first to second quadrant is 180 degrees. Okay, so if you wanted to, you could add 180 to your 81.41, and then that would also kind of give people the idea that your angle is slanted in that third quadrant. Okay, just a lot of different ways to report your answer. Either way, you will for sure be using some inverse trig function of some sort to help you out there. All right, that concludes our fourth one. We're combining angled vectors. We're doing components, we're doing tip to tail stuff, adding stuff, we're using angles, a little bit of everything there. So I hope that was helpful to you in covering our four main topics and mastering all of our main ideas for vectors in physics. Thank you for watching and listening.